um, inductance, a linear inductance, a resistance and a capacitance, and they are in series, and we have a source which is providing a difference of potential, and let's say that this source can change with time. This is a very simple system, and when you apply a potential across, you have the generation of you have the development of a current in this circuit, and let's see how we model it. You see, the same current is going to flow through all these elements. It's going to flow through the source, through the inductance, through the resistance and the capacitance, and it's the same flow. So we can follow the same approach as we did earlier. We will start with a one junction, and this one junction now is going to represent the current. You see, it's going to represent all the bonds that are going to be connected to this one junction are going to have the same flow associated with them. So here we have an I element representing the inductance, the power going from this one junction to this I element, okay. Here we have a source, the source which is providing the difference of potential. We have the C element, and here actually this compliance, same flow, and we have the R element. Again, this is a dissipation. Energy is going to be permanently dissipated. It's not going to be returned back to the system. So we have got here the complete transaction of power shown for this system. Again, let us identify these bonds. We have got them 1, 2, 3 and 4. There are only 4 bonds needed. We can again we can draw the stroke for causality. We have the end which receives the effort. Again, because this end is a source of effort, so naturally the stroke will have to be placed here. We will explain about causality of I and C elements later. So here we have got again all the cause and effect represented on this system itself, and just like before, we are going to have only 2 elements contributing states, the I and the C. So here we have the momentum and the generalized displacement. We have the potential. Now mind you, this V is potential, okay, potential difference. So here we have V. This is now representing the rate of change of momentum. It's electrical momentum, okay. So here you have the rate of change of flux linkage, okay, in electrical terms, because you are having an inductance. So you have flux linkage and you are changing the flux linkage. So the change of this electrical momentum, okay, is represented as an effort. Here you are having a capacitance, and so the effort that is going to be decided by this capacitor is actually, if you assume it to be a linear capacitor, it's Q2 by C, and C is the capacitance. So Q2 is actually your generalized displacement. In the electrical domain, charge is a generalized displacement, okay, and R into I, R into flow. So here we are assuming a linear resistance, just like you assumed a linear viscous element for R in the mechanical case. Here also it is linear, it's obeying the linear Ohm's law, okay. So in this case it is R multiplied by the current, and so you are going to have a drop of potential across the R element. So here you have, because all these bonds are connected to the same one junction, all of them are going to have the same flow. So here you have I element, and what is this I element? It is actually the generalized momentum or the flux linkage divided by the inductance, the value of the inductance. And you know that if you consider it as a linear inductance, so you have P1 upon L. So this is the same inductance in all these bonds. And this diagram, see, you made use of the same elements, okay? They had different connotations in different energy domains, but each of them had an effort and a flow, okay? And you are able to represent them. It is the same bond graph, it looks like, okay? And it certainly means that bond graph can model in multi-energy domains, okay? Using the same set of elements, you can represent models in different energy domains. Your basic alphabet for your language is the same, but now you are able to speak, you are able to represent the same script for Hindi, for Konkani, for Marathi, okay? It's something like that. So in bond graph also, you have the same alphabet, you have the same elements, you have the same power bond, and you are able to model in different energy domains. We have just taken examples, representative examples of the mechanical domain and the electrical domain in this case. Let's take another simple mechanical system, a little different from the earlier one. And in this case, we are going to see how are we going to start. We will start with the motion of this mass, and we have taken the motion of this mass taking a one junction, and on this one junction this one junction is going to represent the velocity or the rate of change of displacement of this mass, okay. I am just considering motion along this dimension only, okay, along one dimension, and so we have a one junction here representing the velocity v1, and it may change with time. Then we connect it to an I element. Why? Because this mass is going to move with this velocity, okay. So directly we place this mass on this one junction. The force that we are applying is also moving with the same motion, it also has the same motion. So here you have the source of effort connected to this one junction itself, okay. Then we look at the other end. So here we have got the force and we have got the motion, the velocity as far as this bond is concerned. Then we have a one junction representing the motion of this end over here, okay. And here this is one junction V0 T, and you see this motion is being imposed by this profile. So it is imposing a motion, so it is imposing a geometry in the form of a geometry. So there is going to be a rate of change of this motion, okay. So here you are having a velocity, and that is being imposed by a source. It's a source of flow. Here on this side you have a source of effort, here you have a source of flow, okay. And across these two ends you have the spring and the damper. Now we are going to make use of a zero junction, and just like a one junction but with a slight difference, the zero junction has all the bonds connected to it. All the bonds connected to a zero junction have the same effort, okay. So we are going to connect the same effort, but in the process what the zero junction does, is it algebraically sums up flows. We saw in the earlier example that the one junction, it has all the bonds connected to it having the same flow, but it sums up, algebraically sums up the efforts. In this case, you have the zero junction, all the bonds connected to it have the same efforts, but in the process, it performs the operation of algebraically summing up flows. Okay? So what it is doing in this case is that it is saying that this flow is equal to this flow minus this flow. That means it is saying that this flow is equal to V1 minus V0. So what you are doing is you are taking the relative motion across the ends of this spring damper combination. Okay? So you are determining what is the relative motion across this. And you know that the same relative motion is common to both the C element as well as the R element, the C element representing this damper, and so we are going to use a one junction because it is common. So we have a C element and an R element connected to this. I hope it is clear to you. Next, let us number the bonds, and we have one placed here, we have two. You can give arbitrary random names or numbers to this. There is no preferred choice. We have done this at random. So we have got 8 bonds here, and all of them have been numbered. Next, we impose cause and effect relations. So we start with the sources always, and in this case we have placed the causal stroke here. Then the next source is the source of flow, and just like a source of effort which imposes effort, here it is a source of flow which is going to impose flow. So naturally a source of flow will be able to receive flow, will be able to receive effort, but it will impose a flow, okay, irrespective of whatever is the effort it receives. So we will dwell on it more. So we have placed causal strokes for the other elements as well, and now our entire model, which is in the pictorial form, is complete with its cause and effect relations also depicted on the bond graph itself. And we are now going to identify how many states are necessary to model this system completely. And what are these states? We know that only I and C elements can contribute states because they are going to keep a track of the history of the system. So we have a generalized momentum P1 associated with this I element, and we have a generalized displacement associated with this C element. That's all. So even for this system, we have only 2 state variables, and only 2 states are necessary to model this physical system. Okay?
Is there any space to ask the question from the participant?
Yes. So I think
Another thing, real life examples of the simple mechanical system, whatever you have mentioned.
yes, actually we will be,
The things this is happening.
yeah, we will be discussing several examples in our subsequent classes, but I feel that I have actually avoided bringing in everything at the same time, you know, because sometimes it could lead to confusion, and I prefer that you get introduced to it step by step. I think in the first part of, in the first lecture,
This is what I am thinking. This is maybe confusing for the participant. If you elaborate the thing simple mechanical system like this and side by side.